Assalamualaikum warahmatullahi ta'ala wabarakatuh and good morning. I'm Dr. Sabah Bau from the Physics Section, Pusat Pengajian Pendidikan Jarak Jauh University Science Malaysia. Uh, this course is JIF 318 Quantum Mechanics. In Chapter 1, Introduction to Quantum Physics. This segment, Unit 1.4, is on the nature of light. We'll discuss photoelectric effect. The objective of this lesson is that you will be able to describe how Planck's hypothesis used by Einstein managed to account for the photoelectric effect. Let us recall the classical light, that means the nature of light in classical physics. By the 1800s, it was clear that well-known phenomena such as diffraction and interference can only be explained only if light consisted of waves. And the principle we use to explain those phenomena is Huygens principle. That means we use the wavefronts as the wavefront as the moving wave principle, and by drawing using compass and protractor, we can determine the wavefront of waves changing in direction in diffraction or in interference. All point on the wavefront is a new source of secondary waves, and basically we can plot on a piece of paper the effect of diffraction and interference by using Huygens wavefront principle. Maxwell ordered equation actually predicts the wave nature of light in the form of oscillating electric and magnetic fields. These fields, electric and magnetic field, are perpendicular to each other, and that explains why light can travel in a vacuum. In the photoelectric effect, we can see that light shining on a metal plate is observed to produce a current. This has been observed by scientists from an earlier time. The current and the maximum energy of the photoelectrons can be measured, and it was found that the current is proportional to the intensity of light. The current produced is proportional to the intensity of light. The maximum energy of the photoelectron, Emax, is proportional to the frequency of the light. So we have two parameters of light here, intensity. One is intensity, one is frequency. Furthermore, there is minimum frequency below which no current is observed. This is what we call as threshold frequency. The second observation is puzzling. In classical theory, the energy put into the system should be proportional to the intensity of light, and the frequency should play no role at all. That's what classical physics says, that the energy should be proportional to intensity and not on frequency. Albert Einstein in 1905 proposed that light behaves as a collection of particles called photons. The energy of each photon is given by h nu, where h is the Planck constant. So basically, Einstein used the proposal by Max Planck by using the E equal to h nu. That means the energy for packets of energy, with packets having energy h nu. In addition, the electrons are bound in the metal with some binding energy, Eb. Therefore, the energy of the photoelectron the maximum energy is h nu minus the binding energy. That's why at certain frequency, there is no photoelectron. There is a threshold. If the energy h nu is lower than the binding energy, that means if the energy of the light, even though you have high intensity light, but if the energy of the photon is low, there is no photoelectron being generated. The fact that Planck constant H appears in two very different phenomena, that is in black body radiation, which we had discussed previously, and now in photoelectric effect, suggests that it has fundamental significance. So Planck constant has a fundamental significance. Fundamental means that it is very in very basic physics. It appears each H or the Planck constant plays a fundamental role in this physical phenomena. Further, it indicates something very radical about the nature of light. It behaves as a particle with energy h nu. So now quantum physics found that a particle or light can behave like a particle with energy h nu. Previously, light is considered as waves only, but now it has two properties. Of course, it has wave properties such as in interference, Young double slit experiment, for example, and in diffraction. But now, in Stern experiment, they found that classical physics using wave nature of light cannot explain the behavior such as this photoelectric effect. So now you can see that light also behave as a particle with energy h nu. In conclusion, Einstein managed to describe photoelectric effect by using the hypothesis proposed by Max Planck. Max Planck proposed that light consists of wave packets each with energy E equal to h nu, and the energy is proportional to nu, which is the frequency of light. Thank you very much for your attention.